Well, the next speaker is Professor Sanjay Mahajane.
I'm here.
Oh, you are here. I'm so sorry. You came from back.
Thank you for inviting me here. I'm really honored to be giving a talk here telling about the work that I have done over the last 25 years. The title says it all. Um, I remember the day I joined here, like in fact I was working in NCL, Dr. Mashelkar was director that time. But before that I was doing my masters in IIT Bombay, Professor Juvekar was my guide, so everyone's here. And I was working in process engineering division and working on processes, and somehow came across this particular article, like which I liked very much, since it tells about how one can combine reaction and distillation in a single unit and get cost effectiveness and compactness to a chemical plant. Okay, so reaction helps distillation, distillation helps reaction. It's a multifunctional reactor. Okay, wherein there's so much reduction in capital cost, so much saving in energy, and so on. So I really thought that it would be great if I get a chance to work in this particular field. And so happened that same period Professor Sharma visited NCL and gave a talk on innovations in chemical engineering, and he mentioned about this particular article, and that's why it went here somewhere. And eventually, after say about 7-8 months, I joined ICT or UDCT that time, like with Professor Sharma as a PhD student, and started working in ionization resin, catalyzed reactions, and so on. That time he was a director, and so he didn't have frequent visits to the lab, so we were lucky. Of course, he used to come once or 2 times in a day and ask reports and all. But again, like he had this uncanny knack of keeping students busy, monitoring the performance, and so on. And I have, of course, before that, this particular example, like about reactive distillation, what's its capacity? It's an integration, process integration, where entire plant can be condensed in a single unit. Okay, where like you have reaction followed by 7-8 distillation columns, and you can do everything in one column. So that's the potential. Okay, so, and that's something I've worked on for the last almost 20-25 years. So coming back to my joining PhD, and we used to have interaction with sir, and then not that frequent, but then of course he had all those chits, and which has been talked about a lot, and I have some proof here, like and there's so many of them, and I don't know, sir, you can remember this. Somehow it's not visible. Anyway, this is about many reactions, and what's the thing that you can do with different types of reactors and so on. We were quite anxious to actually get some inputs from him. Like every day we used to jump on those chits which used to come to the lab and all. One fine day, like he sent this article to us, and myself and my lab mate Aspi, like we thought we would jump on it. In sense, like we liked it so much, and it happened to be my interest, the reactive distillation. And we worked on it so much, and somehow went back and reproduced all the results from this particular group, and went to sir, said that so now we want to publish an article on this. It was too early, probably he knew that, but he wanted to encourage us. He said go ahead and submit it as an independent publication. So we sent it to Industrial Engineering Chemistry, and as expected, probably it came back with a lot of criticisms and got rejected also. So I was a bit nervous, and said that fine, like probably research is not my cup of tea. I went back to him, I said like this is what has happened and all. But he said like give it another try, I think there's a potential in it. And since he said that, we went back and worked on it further, and finally we got this published, and that is during the course of my PhD itself. Like both of us, myself and Aspi, thanks to sir for giving such a motivation, and that's why I'm here today talking on the same topic after 25 years. Then of course, like after joining IIT, like started looking at experimental aspects also, because till then I was working on simulation. In fact, it has its root in again what I did in ICT here, because towards the end, like we built a column. I remember the director's research lab, and we started working on experimental studies in reactive distillation, where sir had asked us to work on butyl acetate, which was a relatively easy system. In fact, that was his peculiar thing, where he used to give simple systems initially to work on so that you generate confidence and all. And that's where like we built a distillation column in which we packed the catalyst and so on. That time there was no commercial catalytic packing available, and that gave us confidence. So when I joined IIT Bombay, like I worked on almost all aspects of reactive distillation. In fact, almost 15 years after I joined IIT, anybody used to ask me like, what's your research interest? I just used to say reactive distillation, nothing else. But then we looked at almost all aspects of reactive distillation. That means right from looking at reaction kinetics, then vapor liquid equilibrium, then there is something called as conceptual design. Then we have this very complicated reactor wherein so many things are happening together. It is not easy to design a particular reactor. That means it's not just like that you determine diameter and height for a column. Like you have to understand the feasibility of it. That means there are so many parameters. You have reactants, you have a choice where to send them in the column, then the catalyst distribution, where should you put the catalyst, where it should be in the, whether it should be in the rectifying section, stripping section, what should be the minimum reflux ratio, what would be the maximum reflux ratio. In fact, reactive distillation has a maximum reflux ratio also. So all these decisions are made in conceptual design exercise, and which uses the knowledge of reaction kinetics and vapor liquid equilibrium. And once you have the answer ready, that you have some configuration ready, you go ahead and actually do experiments in the laboratory. So I built this column. In fact, this is a picture 20 years back. This column is still there in my IIT lab and probably remain there till I retire, because I am quite emotionally attached to it. And actually, after doing experiment studies in column, like you wait for steady state to happen. It's not so easy to actually do continuous experiments in column. You wait hours together to get to a steady state, and so many fluctuations happen and so on. But finally we could crack it. Some of the students mastered that art of getting steady state as early as possible. And then once you get steady state, you combine it with simulations. You have experimentally validated simulator which can be used for further optimization. So all these studies were done in our laboratory, and we worked on many reactions. You can see layer esterification, etherification, dimerization, and so on. And one of the examples I would like to tell you here is of dimerization. Okay, and so I used to call this as a distillation column reactor, and instead of reactive distillation, that means it's a reactor first, okay, and then you are doing distillation to facilitate it. It's not a column in which the reaction is taking place. Actually, there's a difference in these two. So once you say distillation column reactor, that means you have entire reaction engineering domain in front of you. You can do selectivity engineering, you can reduce the catalyst deactivation, you can use energy of reaction and so on. And in fact, you can bring in lot many advantages to actually enhance the overall performance. So coming back to this particular example, this is a reaction of isobutene with isobutene to form diisobutene, and diisobutene has a tendency to react with isobutene to form trimer, then oligomers, and so on. Okay. Now, if you do this reaction in a conventional reactor, you will see that you have selectivity problems, the catalyst gets deactivated, and all that. Okay. So if you do reactive distillation, then you can actually increase the selectivity and so on. So you can see that this is a column. Of course, you have experimental and simulated profile. This is the top section in which we put the catalyst, okay, wherein actual catalyst will see only C4 and not any other product. That means once the dimerization takes place, the product will fall down, and you have very less diisobutene present in the upper section of the column, and that gives you an advantage. The reaction, further reactions are suppressed, catalyst doesn't get deactivated, and so on. There are some results here, and you can see that you get very high selectivity, and of course we have seen the catalyst life also going up. So this is about the process development aspects of reactive distillation. Then we looked at some other things like conceptual design that I was saying. Like, so we did some basic work and looked at geometric methods which were developed by some other groups for normal distillation systems, and then attainable region approach for reaction network synthesis. We combined them and tried to apply it to reactive distillation for selectivity engineering. And there are many series of papers, some students who have really taken efforts and published in that particular work in some reputed journals. Another aspect of it, non-linear dynamic effects, because now you have so many things happening like reaction, distillation, mixing, mass transfer, and so on. And because of non-linearity, you get very interesting behavior in this particular reactor, where like you get multiple steady states, you get oscillations, sustained oscillations, and so on. So if you don't start a reactor properly, then you may eventually get into undesired steady state. And sometimes during the course of the operation also, like you won't know what's happening, because some fluctuations would take you from one steady state to another steady state. So all these effects, we try to explain them for certain reactions like methyl acetate synthesis and TAME synthesis, tertiary amyl methyl ether, and so on. With this, actually, like it's almost 10-15 years I just worked on this particular subject. In fact, like people used to ask me, like this is a very old cow now, how much milk you want from it, like how many publications you are trying to get out of it. Like, so that somehow went back in my mind, and I thought I should do something else. In fact, before joining IIT, I was in Monash University as a postdoc, and of course I was very lucky to have a professor visiting Monash almost for a month every year, and that's when I learned a lot from him actually. And I remember doing many interesting reactions, like especially high pressure reactions under supercritical conditions and all that. Like, in fact, first year was a bit of a lean phase there. I remember when he visited, I actually told him many reasons why I'm not able to do it and all that. But then he really encouraged me. He said at the same time, he said that like fine, like you can come up with many reasons why the things are not happened, but then at the end of the day, the fact remains that the work is not done. But that's something I'll remember forever actually. And I tell this to my students as well. Then we worked on extractive reactions, like distillation. Now you can have an extraction column, and then you can do reactions simultaneously. So we tried propylene hydration, butene hydration, and then cyclohexene hydration, zeolite catalyst, deactivation. All this interesting. It was fun working on that actually. The last one is reactive chromatography. Something of late I have started working on, and last 4-5 years. It's a really interesting reactor, a multifunctional reactor, wherein the reaction happens along with chromatography. So, and again, there is enough scope for doing a lot of work both on modeling, simulation, and experimental studies. So this is a concept, a simple concept where you have products being separated during the course of the reaction, and you can get advantages of conversion and selectivity and so on. But then there is this exciting, fascinating reactor called simulated moving bed reactor. Simulated moving beds are quite common in industry, especially for separations, but not for reactions. And then for reactions, you have to design them properly. So it gives a lot of scope because it is inherently unsteady state process, and you have cyclic steady state happening. So it's a simulation, optimization, so much work. And we did experimental validation also. We have the simulated moving bed reactor in laboratory actually. And so one student came to me one day saying that, sir, we have learned so much about reactive distillation, we have done so much work in reactive distillation, why don't we actually compare reactive distillation with reactive chromatography, okay, and for the same reaction. And I said, why only one reaction? Let's take series of reactions right from C1 to C8 alcohols and do esterification and see like how they behave. So on one side you have reactive distillation, you do optimization, you get experimentally validated simulator, and all optimized results of reactive distillation for a process are compared with optimized results of simulated moving bed. And then you say that fine, which one is better? And you see that some counterintuitive results are obtained here, like reactive chromatography actually competes with reactive distillation for C2 and C3 alcohols, wherein the separation is really difficult because of azeotrope forms and all. Let me stop here. I think Tarat is giving me indication. So finally, I would like to end. It was really fun working. Thank you very much, sir. You actually gave us or showed us a very exciting field of chemical process intensification. It was not just bread and butter for us, but it was something that we really loved and enjoyed working in. And thank you very much. Thanks a lot.
Thank you, Sanjay. Taking ICT culture to IIT, to the domain of IIT. Sanjay has been doing fantastic.